To understand the electromagnet, it's helpful to take a moment to learn a little bit about its inventor, William Sturgeon. William's life was dramatic and inspirational, although his sideburns and hair were a little bit, I think, bizarre. Anyway, take a moment to learn how a retired soldier and bootmaker invented the electromagnet and how the electromagnet works. Ready? Let's go!
Electricity, 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 electricity.
William Sturgeon was born in 1783 in northern England to a poor shoemaker who treated him badly. When he was 10, his mother died, and a few years later, his father basically sold him to another shoemaker who also treated him cruelly. And according to Sturgeon, he lived a life of, quote, slavish drudgery. When he was 19 years old, he escaped by joining the army. The army was good for Sturgeon. He found that the officers in particular were appreciative of his skill at fixing things, especially their shoes. He would also entertain the officers and fellow soldiers with amateur science demonstrations that he made himself. He then traded his skills for lighter duties and to borrow books from the officers. Remember, at this time in England there were no free libraries and books were prohibitively expensive. In this way, he actually taught himself math, Greek, Latin, French, German, Italian, optics, and lithography. After 18 years in the army, Sturgeon retired and moved to the Woolwich district of London. His plan was to start a shoe store. For that reason, he contacted some of the officers he knew from the military. However, many of them were interested in the latest development in science and asked Sturgeon for help with their scientific devices as well as for their shoes. It was fortunate timing because in that same year, Hans Christian Ørsted in Denmark had discovered the current in a wire moves the magnet in a compass. One of the things that was intriguing about Ørsted's experiment was that Ørsted discovered that when the current went down a wire, it would force magnets to point in a circle around that wire. For that reason, Ørsted incorrectly deduced that the current wasn't really going down the wire, but instead was spiraling around inside the wire. In France, a man named Ampere read Ørsted's paper and started to do a series of experiments about electricity and magnetism. For example, Ampere determined that two parallel wires with current in it would feel an attractive force between them. Ampere's experiments were so influential that the current is measured in amps in his honor. One day, Ampere was thinking about Ørsted's theory that current spiraled inside the wire and wondered what would happen if the wire itself was spiraling. Ampere thus coiled up a wire in a helix and studied the magnetism created by the current. The next year, a young Englishman named Michael Faraday published his theory that we still believe today, that electricity is really flowing straight down the wire, and improbably as it seems, somehow creating a circular force field around it. Faraday also stated that the force fields from many wires worked with each other in what Faraday called compound action. For example, Faraday interpreted Ampere's experiment with two wires that feel an attractive force as the compound action of the magnetic fields from the wires supporting each other. Faraday also wrote that Ampere's spiral coil also demonstrated how the fields were additive from parallel wires, as if you look at a coil, it is composed of many parallel wires. Faraday also noted that a coil of wire with current in it acts identically to a bar magnet, albeit a weak one. Let's go back to William Sturgeon. By 1824, Sturgeon's friend had helped him get a job giving science demonstrations to a military academy, so he had the time and money to read Faraday's and Ampere's papers and try to recreate their experiments and even bump them up a notch. One day, he was recreating Ampere's coil and happened to wrap a coil of wire around an iron bar. To his surprise, the iron bar amplified the magnetic effects of the coil. Because the electricity in the wire makes the iron act like a magnet, this object is called an electromagnet. Let's take a moment to talk about a magnet and an electromagnet. A permanent magnet always contains a north and a south. A north and a north will repel, a south and a south will repel, and a north and a south will attract. Permanent magnets also attract certain metals that are not magnets. For example, If a magnet is placed near a paperclip, the paperclip will be attracted to the magnet. This is because the paperclip is made of steel, and steel is composed of little magnets, or magnetic domains, that are randomly arranged. When the paperclip is near a magnet, the little magnetic domains line up, making the paperclip into a temporary magnet, where the north of the paperclip is attracted to the south of the magnet. You know an object is a magnet if it aligns and attracts a metal paperclip. Now let's talk about the electromagnet. An electromagnet is a coil of wire wrapped around an iron or steel bar. Without current, the bar will not attract paperclips or act like a magnet at all. However, if current runs through the wire, then the magnetic fields in the wire align the magnetic domains in the iron or steel bar and make it act like a magnet with a north and a south. The bigger the current, the stronger the magnet. Once you disconnect the battery, the iron or steel basically stops being a magnet. In 1826, Sturgeon found that if he wrapped wire around a U-shaped iron bar, he could create a U-shaped magnet. It was so strong that even with the weak batteries at the time, and with just a few turns of coil, an electromagnet could hold 9 pounds of weight and then drop it dramatically when the current was disconnected. Sturgeon was awarded a silver medal for this discovery, as well as 30 guineas. At the time, everyone thought the big advantage of electromagnets was to make theatrical demonstrations, and they certainly were theatrical. However, it turns out that a magnet that you can control electrically is far more useful and important than anyone knew at the time. In fact, the electromagnet was vital for the discovery of a whole host of electric devices, like the telephone, the electric generator, the radio, the X-ray machine, and the television, to name just a few. One of the first important devices that used Sturgeon's electromagnet was the electromagnetic telegraph. See, in 1827, Sturgeon's paper made it all the way to the backwoods of New York State, where a bored math teacher named Joseph Henry read it and invented the telegraph. Then a racist egoist named Samuel Morse, as in Morse code, stole the ideas and the fame and money. And that crazy story starts next time on The Secret History of Electricity.
Electricity, 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 electricity.
Thanks for watching my video. Please remember to give it a nice thumbs up. It's always a nice thing to do. And I'll see you next time on The Secret History of Electricity. Remember to join my YouTube channel, Kathy Loves Physics, my Facebook page, Kathy Loves Physics, or check out my website, www.kathylovesphysics.com. Thanks, have a good day.